So our next topic is, if n is nonlinear space, if this n is nonlinear space and n dash is a also nonlinear space, then B and n dash, which is a set of all bounded or continuous linear transformation from n to n dash. So B and n dash, it contains all bounded linear transformation from n to n dash. So remember, this is a definition of this set B and n dash, which is a set of all bounded linear operator from n to n dash. Now this is a next theorem, so next result. So what is the statement of this result? If n and n dash are nonlinear space over a CM field F, which is R or C, and B and n dash is a set of all bounded linear operator of n into n dash with respect to linear operation, and norm is defined as norm of T, which is equal to supremum of norm of Tx such that norm of x less than equal to 1, right? So this is a function, here, this is a function, and that is a supremum of norm of Tx such that norm of x less than equal to 1. Our purpose is to prove that this function is a norm. That is our first part. Second part is, if n dash is a Banach space, if this n dash is a Banach space, then B and n dash is also a Banach space, right? Means it is also complete. B and n dash is also complete, right? So there are two parts of this theorem, this result. One is to prove it is a nonlinear space, and second to prove it is a complete by if given is n dash is complete. Now we are going to start the first part. So what is first part? If T belongs to B and n dash, and this function is defined as, this is supremum of this norm of Tx, x belongs to n, norm of x less than equal to 1, right? So this is a supremum of norm of Tx. Now first just understand if this is a nonlinear space and this is again a nonlinear space, and T is bounded operator from n to n dash, right? If this is some point x and this point is T of x, so here it is a norm space, then this type of vector satisfy all the property of norm space, and this n is again norm space, so all x belongs to n also satisfy all the properties of normed. Similarly, Tx, which belongs to n dash, also satisfy all the property of norm. So first remember this thing, because we will use these these statement in the entire part. Now first property, to prove that norm of the functional value of T is greater than equal to 0. Now we know that this is, because that is a nonlinear space, so this is greater than equal to 0 by definition of nonlinear space n dash. So it means the set of these values norm of x less than equal to 1 is also positive, then its supremum is also greater than equal to 0. So what is this? This is a functional value of t. If functional value of t, it is always positive, greater than equal to 0. So this is possible because this term is positive because of n dash. If this term is positive, then its supremum is positive. If its supremum is positive, then this value, this functional value is positive. So that is our first property. Now second property, if this functional value is 0, then it implies by definition supremum of norm of Tx such that norm of x less than equal to 1, which is equal to 0, right? If this value is 0, if supremum of positive number is 0, then it implies each number is norm of Tx is equal to 0, and this is for every norm of x less than equal to 1. Clear? So each number is 0. Now, in order to simplify this result, we already proved in the previous result that there are the three values of this norm of t. There are 3 and 4 equal values of this function. I will use the second value. So second value is this, if this is 0, then it means supremum of this is norm of Tx over norm of x such that x not equal to 0 and this value is equal to 0. If this value is equal to 0, then it means norm of Tx over norm of x is equal to 0. So it implies norm of Tx equal to 0. Norm of Tx equal to 0. It implies Tx equal to 0 for every x belongs to n and x is a non-zero, right? For 0 it is also true. Then it implies t is equal to 0, right? Now reverse this process. If t is 0, then this condition is satisfied, 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 then this condition is satisfied. So what we get? We get if this functional value is 0, then it implies this operator is 0. If operator is 0, then it implies the functional value of t is 0. Clear? So this is the simple case in which we can prove the result number 2. Now, property number 3, which is a triangle inequality. So in order to prove the property number 3, so I take two operators. One is T1, second is T2, and it belongs to B and n dash, right? So it is a bounded linear operator. Now this norm of this is a functional value of T1 plus T2. So which is equal to supremum of this is this T1 x plus T2 x. Clear? I used one step norm of x less than equal to 1. Clear? Right? So here in the first step it was T1 plus T2. It was T1 plus T2 of x. So it is converted into T1x, so T2x. So don't confuse yourself. So that is the simplified form. Now this part and this part, this vector and this vector belongs to n dash. N dash is a norm linear space, so it satisfies all the property of norm. So that's why, so this is less than equal to supremum of T1x such that norm of x less than 1 plus supremum of T2x, which is norm of x less than equal to 1. So this is less than equal to this value plus less than equal to this values. So it satisfies the triangle inequality T1 plus T2, which is less than equal to norm of T1 plus norm of T2. Clear? So which prove the property number 3. Now after that, property number 4. So we take some scalar which is a alpha. So property number 4, let alpha be any scalar. So this is any scalar. If alpha be any scalar. If alpha be any scalar, so norm functional value of alpha t can be written as supremum of norm of alpha tx such that norm of x less than equal to 1. It implies supremum of, so this can be written as absolute value of alpha norm of tx such that norm of x less than equal to 1. Now this number is positive. If this number is positive, so we can take it outside, then supremum will not change. So it implies absolute value of alpha supremum of norm of tx norm of x less than equal to 1. So this is absolute value of alpha into norm of t. So it satisfies the fourth property of norm. So this is absolute value into norm of t. Then it means this is a norm on B and n dash. Then B n n dash is a normed linear space. So it was a already vector space. So we define some function to prove that this function is a norm. Then it means this is a norm linear space. So it proved this Bn dash is a norm linear space. Now after that, our purpose is if n dash is a complete, then B and n dash is also a complete. Now second part. In second part, given is n dash is a complete space. So which is a complete space. To prove B n n dash is also a Banach space, or we can also say that it is a complete space. So we can take any of the values. Now to prove this set, this space is complete, so first we take a Cauchy sequence. So let Tn, which is a Cauchy sequence, in Bn n dash. So remember that it is a bounded linear operator because it belongs to Bn n dash. And second, because of Cauchy sequence, it implies norm of Tn minus Tm approaches to 0 as Mn approaches to infinity. So remember this result. This is a result of Cauchy sequence, right? Now, from this result, we can also find another result for each x belongs to n, right? So norm of Tnx minus Tmx, this can be written as norm of Tn minus Tmx. We know the property of a bounded operator, so that means this is norm of Tn minus Tm into norm of x, right? Now by property number 1, this approaches to 0 as Mn approaches to infinity. So just remember, so for x it satisfies these values. It implies this Tnx for every x belongs to n, which is a Cauchy sequence in n dash, remember, because this is a part of n dash. So this is a Cauchy sequence in n dash. What is n dash? By given part. So it is a complete. If it is a complete, then every Cauchy sequence is a convergent in n, right? Now, if n dash is a complete, so this is a convergent, then it implies this sequence Tnx, which is a convergent in n dash. What do you mean by this? It means there exists some Tx belongs to n dash, there exists some Tx belongs to n dash such that Tnx approaches to Tx as n approaches to infinity. So which is equation number 3. I think it is equation number 3. Clear? So here we used the benefit of completeness. Now see that we find a sum operator T. We cannot say that it is an operator because just we find a Tx member of n dash. So what is Tx? Tx basically it is a limit of n approaches infinity, Tnx, right? X is member of n. So T is a sum operator that we define. So we define T is some function from n to n dash which satisfy this condition, right? So here now it is a mapping, but my purpose to prove it is a operator. So the condition of operator is it is a linear transformation, also it is a bounded. So first I prove that it is a linear transformation as well as bounded. Now let x and y, these are two vectors from n, and alpha and beta are two scalars, and alpha, beta are two scalars, right? So what we get? We get T of alpha x plus beta y by definition, by this definition. This is a limit n approaches infinity, Tn alpha x plus beta y, right? Now what is Tn? This Tn is a linear operator. Because it is a linear operator, so it satisfies limit n approaches infinity, alpha Tnx plus beta Tny. Remember this, right? So that is in bracket. So this value can be written as alpha limit n approaches infinity Tnx plus beta limit n approaches infinity Tny, this values. So what is this? It is a T of x. What is this? It is a T of y by using this result. So this will become alpha Tx plus beta Ty. It implies T is a linear transformation. It means it is a linear transformation. So it is our first part. Now second, to prove that it is a bounded. Now to prove it is a bounded, our purpose is to prove that norm of Tx is less than equal to this values, right? Less than equal to that values. Now we already aware about the property norm of Tn minus norm of Tm, absolute value less than equal to norm of Tn minus Tm, right? And because of Cauchy sequence, it approaches to 0 as Mn approaches to infinity. So it implies absolute value norm of Tn, norm of Tm. This approaches to 0 as n approaches to infinity, m and n, and again it implies this is a sequence of norm is a Cauchy sequence in field. Cauchy sequence in field. Field may be R, field may be C. And in both cases, field is complete. Field is complete. So this sequence will be convergent, right? Because every convergent sequence is bounded, so this sequence will be bounded. Remember this. If this sequence will be bounded, then by definition of bounded, there exists a some positive number k such that norm of Tn less than equal to k, right? This values. So what we get? We get norm of Tn x, this values, norm of Tn x, this values, clear? So this is norm of Tn x. My aim is to prove that the norm of Tx is a norm of Tx, that T is a bounded, clear? So we will use, since Tnx is a bounded operator, so it means the norm of Tnx can be written as norm of Tn into norm of x, which is less than k into norm of x. So remember this result. But my purpose to prove that this should be a bounded. So what is this? This is a, by definition, limit n approaches infinity Tnx, right? Norm is continuous function, so we can take limit outside. Limit n approaches infinity, norm of Tnx, this values, by using this result. By using this result, this is less than equal to k into norm of x. So it implies norm of Tx less than equal to k into norm of x for every x belongs to n, and it implies T is bounded operator. So this is a definition of bounded. So T satisfies both the properties. One, it is a operator, means linear transformation. Second, it is a bounded, so it implies T is part of Bn n dash, right? Clear? So T is part of Bn n dash. My purpose is to prove that Tn, T norm of Tn, or we can also say that Tn approaches to T. That's all. That my purpose is. So just remember my purpose, that is Tn approaches to T. So that is a rough work. So that is a just rough work. So see that. So what is this? Will be approaches to T if norm of Tn minus T approaches to 0, right? So what is this? By definition, it is a supremum of norm of Tnx minus Tx such that norm of x less than equal to 1 approaches to 0, right? So that is my purpose. It means I should start my question from this condition, from this values. What is this values? Let x belongs to n with norm of x less than equal to 1. I start my question from this values to prove my result. And second, my purpose is to prove this part approaches to 0. To prove this part approaches to 0. Now to prove this part, what is that part? That is a norm of Tnx, norm of Tnx minus a Tx. So this part approaches to 0. So that we already proved that this is a convergent Tnx which is convergent to Tx. That we already proved that, but that we proved for the x belongs to n. Here condition is norm of x is less than equal to 1. So remember only this fact. Now let n is greater than equal to n naught. Suppose it may be n naught, it may be n. If n is greater than equal to n naught, then we know that two conditions. One is the convergent value of that Tn of x minus Tx, that can be written in this way, and second is the Cauchy sequence. So remember all the two values that we will use in this function. The norm of Tnx minus T of x, these values. So this can be written as Tnx. Here I can also take the value of m or any other values. So I take n0. So this is a Tn0 x plus Tn0 x minus Tx, and this is a norm, right? So by using triangle inequality, so this is less than equal to norm of Tx minus Tnx minus Tn0x plus norm of Tn0x minus Tx, this values, right? So this is the value, this that we find it. Okay, this value is there. Now by using the result of Cauchy sequence, this term approaches to 0 by using the result of Cauchy sequence of Tnx, and similarly by using the result of convergent, this approaches to 0. Also we can say that it is less than equal to epsilon by 2. So also write it as norm of Tn minus Tn0 into norm of x, right, plus here norm of Tn0 x minus Tx, right? So this values. Now from this, by using the concept of Cauchy sequence, this term is less than epsilon by 2, this term is less than epsilon by 2, and similarly by using the concept of convergent, this term is less than epsilon by 2. So using that result. Now first, since Tn is Cauchy sequence, we know that as Mn greater than equal to n0, it implies norm of Tn minus Tm, which is less than epsilon by 2. This is result of Cauchy sequence. And second result is, if n, this nx n0, n is greater than n0, then it implies this values norm of Tnx minus Tx, which is less than epsilon by 2, right? Where for epsilon greater than 0, for epsilon greater than 0, there exists a positive integer n0 such that it satisfies this condition, for it is 4, and this condition because it is 5. Suppose. Clear? So this result is due to Cauchy sequence of Tn, and this result is due to convergence of T and X. Clear? Now norm X is less than 1, so this term is epsilon by 2 plus, and by 5 this term is also epsilon by 2. So total term is equal to epsilon. Clear? So what we get? We get norm of T n x minus Tx. X belongs to n, norm of X less than equal to 1, this set, and this set is less than epsilon. Remember, if the entire member of this set is less than epsilon, then its supremum is also less than epsilon. Right? It implies, what is that supremum? Which is a norm of Tn minus T less than epsilon, and this is for every n greater than equal to n naught, n greater than n naught, for every n greater than n naught. So it implies this Tn convergent to T. What is T? T belongs to Bn n dash. So we take it is a Cauchy sequence in Bn n dash and prove that it is convergent in Bn n dash. If it is convergent in Bn n dash, then it implies Bn n dash, this is a complete. If it is a complete, so it is a Banach space. So normally it is a non-linear space, but if in the given part n dash is a complete, then Bn n dash is also a complete and also a Banach space. Now next definition is equivalent norm. Next definition is equivalent norm. So what is the norm? So this is a equivalent norm, right? So what do you mean by equivalent norm? We can one norm, suppose this is denoted by this one, second norm which is denoted by 2, suppose, and this notation is used for equivalent, right? So this is a norm 1 is equivalent to norm 2, norm 2 is equivalent to norm 1. If there exist two positive number A and B such that two positive number A and B such that it satisfies this condition: A norm of X less than equal to B norm of X. So here it is norm 2, here it is norm 1, here it is norm 1. So norm 2 for every X belongs to n. So what is n? N is normed linear space. So X is vector of non-linear space. So if this condition is satisfied, then it means that these two norms are equivalent. They behave a same. So it means if this any sequence is Cauchy with one norm, and it is also Cauchy with second norm because of the equivalence. So this is a definition of a equivalent norm. So in order to prove that definitions, prove that statement, so we will have some proof, so that we will do later on. Now, so just remember here the definition of equivalent norm on a nonlinear space. So that is very, very important.